I gave this title of Entropy, Information, and Alchemy. We'll see if I get to everything. Um, the primary focus of what I'm going to talk about is entropy, how entropy can be exploited to create structures that we're interested in, how information can be encoded in these structures, and how we can use entropy to encode information. And then I'll talk a little bit about how we can combine those two things to do a type of alchemy I call digital alchemy, which is to use computer simulations to identify particular types of building blocks that are optimized for obtaining certain types of target structures. So we're going to talk about those structures and how we do this. So this is a movie of a Monte Carlo simulation. So this is a stochastic simulation of a system of octahedra, mathematically perfect, regular, hard octahedra that are at a fixed number of particles in a cubic box with periodic boundary conditions. The box is allowed to actually change shape and size. And what's happening is that the particles are being randomly chosen, randomly translated and or rotated some small amount. If doing that would cause an overlap in the system, we reject the move. And if it doesn't cause an overlap in the system, we accept the move. So what's going on is that these particles are moving around in a stochastic fashion throughout the box and exploring the total phase space that's available to the system at a fixed density. What we're seeing here is that when the particles are colored blue, they're in a fluid configuration. So there's no long-range order in the system, very little short-range order in the system. And when you see yellow, the particles have spontaneously formed a locally ordered structure, and that locally ordered structure grows to take over the entire system and end up in a crystal. So this is going to be, so have this in your mind as I'm talking. What's fascinating about this seemingly very simple system is that this system is undergoing a first order thermodynamic phase transition from a fluid state to an ordered crystal state with nothing but entropy and entropy maximization. There are no forces between the particles other than excluded volume interactions. And what I hope to show you is there's an incredible richness and diversity in this, and a lot of things that I think are underappreciated about entropy. So let's stop and talk about entropy for a minute. So when we first learned about entropy in high school or college, we learned about it associated with heat, that every kind of a process always loses some energy to heat. And that lost ability to do work we called entropy, because Clausius called it entropy. That should say the 1850s, sorry, right there. So Clausius called that entropy in the 1850s. But no, that's wrong. Clausius was much older than that. Sorry, it was a typo. Okay, so that was at the time of the steam engine. All right. So Boltzmann and Gibbs, though, were the first to identify this concept of entropy that Clausius had identified and Carnot had applied to the heat engine, and thought of it as a way of counting the number of states in what they called state space, which is the volume of allowed microstates available to a system. So let's define that better. So this is the familiar, to many of you, expression of the Gibbs entropy. It says that if you have any system, take any system, you can write down the entropy of the system by summing over all of the possible microstates available to the system, all of the possible configurations. So in the box of octahedra that I showed you a minute ago, that means every possible position and orientation of every particle in the system that's allowed, which means everything, any possible snapshot of the system in which there's no overlap of the particles. That's an example of an allowable microstate. You count over all of the allowable microstates, weighting them by the probability of finding that microstate times the log of the probability of finding the microstate. The minus sign is there because probabilities are less than 1, and so that way entropy is always a a positive number. Okay. Some of you may be more familiar with the von Neumann entropy, which is an extension, a generalization of the Gibbs entropy to a quantum, from classical system to a quantum mechanical system, where now you have a quantum mechanical system that's described by a density matrix, rho, where you can write this in terms of its eigenvectors, where these eigenvectors, these are the eigenvalues, and this is the actual microstate of the system. But again, you have an expression for your entropy that looks very similar to the Gibbs expression for the entropy. And when you have a completely pure space and not a linear superposition of states, then the entropy is defined to be 0. So the von Neumann entropy is a measure of the departure of a system from a pure state. Now, Shannon came along, now in the 1950s, and invented information theory. And von Neumann convinced him to name his measure of information entropy. So we call that Shannon entropy. And again, it has this similar form. If the Shannon entropy is now measuring the uncertainty that's associated with a random variable. So it's like the amount of information in a message measured in bits. So you could think of Shannon entropy as the minimum number of yes/no questions that you have to ask to fully determine a system. Okay, so like if you're playing, say, 20 questions, and I say I'm thinking of a person, and you get to ask me only yes/no questions, right? You could just randomly shout out, is it Gandhi? Is it Madonna? Is it Britney Spears? Is it von Neumann? Is it Jim Simons? I was getting there. But that would, of course, be silly because you'd have to ask a lot of questions, and maybe hopefully you do it. So the first thing you'd probably do, you'd say, is the person you're thinking of a woman? Because you cut out half of the possibilities, right? So you think of the strategic questions that you would ask, the minimum number of questions that you could ask to get to the answer that you want. That's the Shannon entropy. Okay. So if you think of a coin toss, if you have a coin that's perfectly fair, then that's the maximum entropy situation, because the best you can do is guess that the next coin flip would be a heads or a tails, but you would only be right with probability 1/2. If I gave you a biased coin that was 2 heads and no tails, then you could guess that it would be heads with probability 1, and the system would have 0 entropy. Okay, so that's a way about thinking of entropy in the context of information. Now, I want to think about this in this system of these hard particles that I showed you. So consider that you have a completely closed system where there's no exchange of information with the environment. There's no thermal bath. It's a completely isolated system with a fixed number of particles and a fixed volume at a fixed total energy. When you have a closed system like that, all microstates are equally likely. If you take that expression for the probability of a given microstate and you just put that into the Gibbs expression, then you get the familiar Boltzmann expression that the entropy is equal to a constant, which we call the Boltzmann's constant, times the log of the total number of microstates in the system. So that really captures how the entropy is just a measure of the total available phase space of the system. And the reason why this is so interesting is because if you think of entropy not in terms of lost ability to do work, but as really just counting possible microstates of a system, then a maximum entropy situation will be one that maximizes the number of possible microstates available to the system. So typically, one thinks of entropy as associated with disorder. But it shouldn't be associated with disorder in the sense of spatially disordered. So if you look at a fluid, like the blue phase of particles in the fluid phase, and you look at it in the crystal phase, you'd say, oh, the fluid is more disordered than the crystal. The crystal, I can see where all the particles are. They're all lined up in a lattice. And in the fluid, they're not. So the fluid is more disordered. But what happens is that if there are more microstates available to the system when it's ordered than when it's disordered, then you can order things just by entropy maximization. So that's what we're going to look at. So Onsager knew this. In 1949, Onsager argued that if you took a bunch of rods, hard, impenetrable rods, and you crowded them enough, then they would give up translational entropy, they would give up rotational entropy for translational entropy in order to maximize the entropy of the system at a given packing fraction. So a system of hard rods would go from a fluid disordered-like state to an aligned liquid crystal, pneumatic liquid crystal state simply by maximization of entropy. So that's not so surprising when the objects are elongated. You can sort of see how you crowd them together, and in order to crowd them more, they have to align, okay? What was much more surprising was when Kirkwood, a chemist in the 50s, said, you know, the same should be true for simple hard sphere systems, that hard spheres should be able to undergo a fluid to crystal phase transition due solely to entropy maximization. And this was something that did not at all gain immediate acceptance until his students Alder and Wood, Alder working with Wainwright and Wood working with Jacobson, did what were the first. Alder did what at the first was the first molecular dynamics simulation of a hard particle system. Wood did Monte Carlo simulations. So in the molecular dynamics simulations, they just basically solve F equals ma, and in the Monte Carlo simulation, they're doing it stochastically, like in the example that I showed you. And sure enough, they showed that it went from it underwent a disorder to order transition. So red is when the particles are locally disordered. Green is when all of a sudden they become aligned with their neighbors. It turns out that hard spheres will order into a face-centered cubic crystal. And this is at a fixed volume fraction, fixed packing fraction of particles in the box of about 50%. So you just start out 50% and they spontaneously order with no attraction between the particles whatsoever. And that's because there are more ways of arranging the particles in a pattern that is consistent with that of a crystal than there are with that of a fluid, which to many people, including me, is really counterintuitive. But that's because if you look at these particles, if you look at the crystal, I can wiggle these around. I can move them slightly and still have a pattern that's consistent with a crystal. So this idea of entropy maximization requires that you have thermal motion in the system. The system must be able to explore, in principle, all possible microstates that are available to it. For that, it needs thermal energy. So there's this wiggle motion that's going on. If it doesn't have that, if it can't explore all of its possible microstates, then you don't have this phenomenon. Okay, now I want to compare this idea of spontaneous disorder to order transition, which we call self-assembly. So crystallization, just like the freezing of water into ice in your freezer, is an example of a self-assembly process where the molecules self-organize themselves into the ice crystal. Or here, our hard spheres self-organize themselves into a face-centered cubic crystal. I want to compare that with the packing problem. So the packing problem is this age-old problem of great interest to many to physicists and mathematicians alike, and uses it as an example the case of hard spheres. So the Kepler conjecture, right, was that the densest that you could possibly pack spheres together was pi over the square root of 18, which is 74.05%. So Kepler conjectured that in the 1600s. It wasn't proven until 2005 by Hales that in fact is the densest possible packing of spheres. And it turns out that to achieve the densest packing of spheres, you have to pack them into the same crystal structure that they also happen to self-assemble into at much lower packing fractions than 74.05%, down around anywhere above, say, 50% packing fraction. It turns out that they're forming the same crystal structure. As we'll see, that's not always true. The difference between thinking about packing problems and assembly problems is that when we think about assembly problems, so in either of these, we're minimizing free energy. In a thermodynamic system, we must minimize free energy. When you have no and in both cases, I'm going to consider no hard interaction, no interactions between the particles other than hard excluded volume interactions. When you're maximizing, so in an assembly problem, minimizing the free energy in an NVT ensemble is equivalent to maximizing the entropy, okay? But when you're talking about maximizing, when you're talking about packing, you're increasing the pressure of the system. You can think of it in a different thermodynamic ensemble where you hold pressure fixed instead of volume fixed. And then you have the Gibbs free energy that you must minimize. So you have contributions from both the entropic contribution, but you also have this enthalpy contribution from the pressure times the volume term. And it turns out that when you, of course, try to pack and you're squeezing these particles closer and closer together, your pressure is getting very, very large. And so this term outweighs the entropy term, and the solution to minimizing this free energy is minimizing the volume of the system, which means maximizing the density. So the solution to what is the densest I can possibly pack any, say, convex shape, the answer is the one that maximizes the one that maximizes the density. That's because it's the one that minimizes the free energy. So it means that if you take a thermodynamic system that spontaneously self-assembles into some structure, that structure might be the structure that maximizes the density at infinite pressure, but there's no reason it has to be the same structure. Okay, so we got into this problem in 2007 or something like that because we looked at hard tetrahedra. The simplest Platonic solid, a mathematically perfect regular hard tetrahedra, threw them in a box, did the same kinds of simulations basically that Alder and Wainwright did in 1957, only in a bigger system and more efficiently. But what came out was a huge surprise to us because what we found, and this was really against everyone's intuition, is that hard tetrahedra also spontaneously order into a crystal, but instead of an FCC crystal, they spontaneously ordered into a dodecagonal quasi-crystal, which just was completely surprising to us. So this is a picture of, so this is what the system actually looks like when it orders. All of the particles are the same, but we color them so that you can identify these motifs. What's fascinating is that the particles spontaneously organize at about 52% packing fraction into these pentagonal dipyramids that you see here. And underneath that is a ring of 12 tetrahedra, up, down, up, down. And then underneath that is another pentagonal dipyramid, another 12-member ring. Now, if there was a 10-member ring, and I had a pentagonal dipyramid top and bottom, I'd have an icosahedron. But that's not what it does. Instead, it forms these 12-member rings. And it turns out that so if you look at it, so this is the 12-fold rotationally symmetric direction, and I'll show you the diffraction pattern in a minute. This is it from the side. There are two classes of quasicrystals. There are icosahedral quasicrystals that are full three-dimensional quasicrystals, and then there are these axial or planar quasicrystals that can be 8-fold symmetric, 10-fold symmetric, 12-fold symmetric. And this one is 12-fold symmetric. So axially symmetric means that it's quasicrystal along this one axis, but in two dimensions. But if you turn it, it's periodic. So this is looking at it now along the periodic direction. And here are these columns that I mentioned, where you have a pentagonal dipyramid and then a ring, and then the pentagonal dipyramids are hidden inside. You can't really see them, but they're making these things. Now, if we were to set this up where So you might think, look, it would be way tighter packing if I had a 10-member ring, because a pentagonal dipyramid fits perfectly, well, not perfectly. It fits much better into a 10-member ring. You get an icosahedron that has a gap of 1.54 steradians. So it's a packing of about 89%. So it's really dense packing in an icosahedron. If you set the system up like that, it melts, falls apart, and reforms into a much less packed system, but it has higher entropy. So this is what the bond order diagram looks like of the system. This is a pattern where you stand on a particle and you look at your nearest neighbors and you project them onto the surface of a unit sphere, and it acts as a fingerprint of what your system is. Along with the diffraction pattern, this shows it along the 12-fold symmetric direction, and you see this pattern of rings with 12 Bragg peaks that signifies that this thing is a quasicrystal. It turns out that this quasicrystal that formed is isostructural to a quasicrystalline chalcogenide formed from tantalum and tellurium that was discovered in 1998. And if you take our diffraction pattern and overlay it on top of their diffraction pattern, then you see that it's basically the same structure. So this is really remarkable. In the quasicrystal community, so first of all, most quasicrystals are made of metals like tantalum and tellurium, vanadium, copper, nickel. You always have to have at least 2 types of atoms to get these interesting aperiodic quasicrystals that are rotationally ordered, but have no long-range translation order, no unit cell that can be repeated in the system. And so the idea that you could get such a complex crystal structure from the simplest platonic solid and entropy arising from simply thermal motion is remarkable. One of the ways that you identify a quasicrystal is by looking for tilings. And so if you look at our picture, so this is almost the same picture we saw before, but with different colors, you can identify that if you connect the centers of these pentagonal dipyramids, you can make squares and you can make triangles. And so this dodecagonal quasicrystal is a tiling of squares and triangles. Every quasicrystal has, in particular, planar axial quasicrystals have what are called periodic approximants. So if you were to take those square and triangle tiles and pick them up and then put them back together again in a regular way, that would give you a translationally periodic crystal structure. Then you have this periodic approximate, and you can have first order, second order, higher order periodic approximants that have larger and larger and larger unit cells. In principle, you can construct those. So the nearest periodic approximate to our quasicrystal is this one, where you arrange the triangles and the tilings in this and the squares in an Archimedean tiling, the 3-4-3-2-4 Archimedean tiling. It's also called the sigma phase. It has 4-fold symmetry instead of 12-fold symmetry, so you can really tell the difference if you have a quasicrystal or if you have its periodic approximate. It's remarkable that this periodic approximate has 82 particles in the unit cell. We never see it on our simulations, but I'll show you some information about that in a minute. So now let's talk about the packing problem. So what is the densest packing of tetrahedra? We saw that the densest packing of spheres and the self-assembly of spheres gives you the same structure. What about for tetrahedra? So when we found this structure, we compressed it in our simulations, and we found that the densest we could possibly compress it was 85.03%. Now, whenever you read papers about densest packings, they're very hard to prove, to provide a mathematical proof of what is the densest packing. So Hales did this for spheres. It's not been done for any other convex shapes. But the densest packing of tetrahedra actually has a very long history. And so I love this slide. My student Pablo Damasceno made this slide for me some years ago that shows the history of the tetrahedra packing problem on a timeline that's very compressed. So you can find writings from Aristotle where he was associating various shapes with the heavenly bodies, and said that and he called them prisms at the time, but later interpretations felt that he was talking about the perfect tetrahedra. He thought that tetrahedra could fill all of space, but they can't. But that wasn't really recognized till Johannes Müller, aka Regiomontanus, in the 1400s. And so that was the first time that they realized, oh, it doesn't fill space. So what is the densest packing if it's not 1? You know, if you take cubes and you densely pack them, you have a packing fraction of 1. But what is it for tetrahedra? So Hilbert got very interested in the problem. He put it, it's a special subset of problem number 18 on Hilbert's list of mathematical problems. He got Gromer and Hoylman interested in the problem. They posed the problem as the densest lattice packing. So rather than just saying, what is the densest packing, they said, what is the densest I can pack tetrahedra if I only allow 1 particle in the unit cell, which just amounts to how do you orient them to get the densest packing with 1 particle in the repeat unit. And so they came up with this, so actually I skipped Minkowski. Minkowski actually came up with a wrong answer of 9/38. Hoylman and Gromer got a better answer of 18/49. That is the densest lattice packing, but it's not the densest packing of tetrahedra. Okay, so then nothing much was done with hard tetrahedra. Ulam came along in 1972, Stanislaw Ulam, and he didn't say anything about tetrahedra. He said in some remark at some conference, and it's recorded in a book by Martin Gardner, but there's no paper you can find by Ulam on this, where he said, I bet that spheres are the worst packers of all convex shapes. That if I take a convex shape and try to pack them, I can never pack any convex shape. I can pack all convex shapes more densely than I can this sphere. Okay, fine. So that was interesting until about 2006. Conway and Torquato said, you know, I bet you that the tetrahedra could be a candidate to violate Ulam's conjecture. That tetrahedra, if you look at these numbers, might pack worse than 74.05%, or pi over the square root of 18. And so they started constructing dense packing. So they said, well, I know that I can take tetrahedra and put them in icosahedron and pack them at 89%. That's really high. Now let's pack these icosahedra. Well, it turns out that they couldn't beat 74.05%. They couldn't even they got around 69, 68, 69, 70% packing fractions. They tried all kinds of other things, Welsh bubbles, Scottish bubbles. They weren't able to get better than 74%. Along came a brilliant young mathematician by the name of Elizabeth Chen, who's now a postdoc at Harvard. She was a graduate student in mathematics at the University of Michigan. And we were working completely independently of her. We discovered her completely by accident later on in the story. For her PhD thesis, she constructed a packing of tetrahedra, spurred on by her advisor, Jeffrey Ligarius, who showed her the Conway-Torquato paper and said, I bet you can do better than that. So she analytically constructed a packing of nonomers where she took a pentagonal dipyramid and another one with a missing tetrahedra, put them together, then you get this nonomer. And she packed these nonomers. She did this numerical construction and said, you know, I'm going to assume you can. I'm going to pack it like this, and I'm going to show that packing is an allowable packing. And she did that, and she found a packing of over 77% packing fraction. It turns out you can compress that to like 78, 79%. But it was the first demonstration that tetrahedra packed denser than spheres, and that was great for Ulam. So Ulam still stands. Okay, so if you see this, it goes from millennia to centuries to decades to years. So she did this work in 2007, and then you can start to see months and then days, and literally it was down to minutes at the end of this story. And so then we're doing our work where we weren't trying to look at densest packings at all. We were studying entropically driven self-assembly. And we happened to get this phenomenally complicated and dense packing that we were able to densify, compress up to over 85% packing fraction. So we thought, surely that is the winner. That is the densest you could possibly pack hard tetrahedra, although there's still no mathematical proof of that. At the time that our paper was in press, another brilliant young mathematician by the name of Yoav Kallis, who worked with Veit Elser at Cornell and is now a postdoc at Santa Fe Institute, he constructed with Veit Elser a packing, and I'll show you this packing. Come on. Oh, that arrow is breathing, so I remember to mention Ulam. Just a second. It's supposed to breathe 13 times. Okay, there. So this is what Yoav said. They proposed this construction that you take two tetrahedra and make a dimer out of it, and then take the anti-dimer. So basically construct the Kuperberg pair. And they were able to show that this packs with a packing fraction of 100 over 117, which is 85.47% packing fraction, which beats 85.03%. So that was now the densest packing of hard tetrahedra. And what's remarkable is that it's so simple. There's 4 particles in the unit cell instead of possibly 82 particles in the unit cell. So to me, that makes it absolutely berserk that the system would choose to self-assemble into such a complicated structure when it could have just done that. Okay, so then it turns out that they didn't tweak it enough. They didn't have it quite right. Their proposal was a monoclinic structure. Torquato and Zhao proposed basically generalized their packing and got a slightly higher number. And then that was when we then worked with Beth Chen, and we put a few particles in a box, compressed it. We're able to get a packing that instead of being monoclinic was triclinic. Beth took that packing and showed and constructed the intersection equations and proved that that was an allowable packing, and that allowable packing matched to 1 part in 10 to the 5th our simulations, which gave 85.63% packing fraction. That is now the densest you can pack tetrahedra. Nobody's been able to pack them more densely than that. Yoav, Callas, and Veit Elser have a mathematical proof demonstrating that the packing must be less than 1. But there is no, so we have an upper bound, but we don't have, but we have no proof that of what it might be. So it might be even higher than that. Okay. So I mention this because the question is why? Why would the system prefer such a complicated structure to self-assemble into when it could just make this dimer crystal? And the answer, of course, is entropy. So in computer simulations, it's possible for us to actually go in and calculate the entropy difference between different structures. So we could set up our system in the dimer crystal and the quasi-crystal or its periodic approximate at the same densities and calculate the free energy difference and see which one is lower. Or entropy difference, see which one is higher. Whichever one has the highest entropy wins. So we did that. And so here it is as a function of pressure. This is what we call the equation of state of the system. It shows at a given pressure that you set the system at, and the system's allowed to change its volume and change the symmetry of the box that it's in, and you get out an equilibrium packing fraction that corresponds to that pressure. And that gives you this equation of state that you see at the top. So that allows us for every pressure to see what the packing fraction is. And then this is the difference in the entropy. And what it shows us is that the dimer crystal has a higher entropy only at these crazy high pressures where the density of the system is greater than 84%. So the whole reason why is that by self-assembling into this crazy quasi-crystal structure, the system has far more entropy than it would if it self-assembled in a dimer crystal until you get up to densities that are so dense that you could never see it kinetically. But mathematically, it actually starts to have a higher entropy, and then that also is the one that has the highest density in the limit of infinite pressure. So this idea of the spheres having FCC in both cases is up here. Right here, there's another intervening structure that's stabilized by entropy. Okay, so that's an intro. So that gives you the kind of the meat of the problem. What we then did is we said, okay, now we know everything there is to know about tetrahedra. Is this just a fluke that tetrahedra form very interesting structures? We have spheres, we have rods, cubes self-assemble into cubic crystal structure, and we have these crazy tetrahedra. Or is it just the tip of the iceberg? So I have these very ambitious student and postdoc, Pablo Damasceno, Michael Engel, who redid the whole tetrahedra study for 145 different shapes, all the the other Archimedean solids, the other Platonic solids, the Archimedean solids, they're mathematical duals, the Catalan solids, they're 92 Johnson solids. They did a bunch of prisms, antiprisms, and zonahedra. And each one studied the same way that we studied the tetrahedra. And it was incredible, the diversity of crystal structures that we got out and the complexity of some of those structures. It turned out that 101 out of 145 of them self-assemble somewhere between 50 and 65% packing fraction into a crystal structure, most of which are different from their densest packings. What we are trying desperately to do is to connect the shapes of the particles and the symmetries of the particles to the structures that come out. So here are some examples. So this up here, that shape up there forms a cubic crystal. There's the Johnson solid number 26 forms the beta tin structure. Johnson solid number 18 forms the body-centered cubic crystal structure. This truncated augmented dodecahedra forms the gamma brass structure with 52 particles in the unit cell. That was one of the more complex ones that we found. So these are all isostructural too. If I put my centers if I look at the centers of the particles, it's the same crystal structure as I would get from the atomic equivalents. So clearly you can see that if you just looked at the shapes of the particles, in very few cases would you be able to guess what they would want to either self-assemble into or pack into. Here are some of the more complex crystal structures. I mentioned gamma brass, the beta tungsten structure, beta manganese structure with 20 particles in the primitive cell from a perfect dodecahedron. Very interesting structures. And then we were able to classify them, and it turns out that 44 of them I mentioned, we could not get them to self-assemble into anything. What's fascinating is that for every shape over here that does form something, you could find a shape over here that's very similar to it and just doesn't form anything. So what we do is we can take those shapes and homologously tune some shape parameter and see where does that start to fail. Also, you can look at this and say, all of these 66 dark blue shapes spontaneously self-assemble in a face-center cubic crystal. Why is that the maximum free energy structure? For some of these, they look like spheres, so it's not so surprising. But for many of them, the densest packing is not face-centered cubic. For some of these, you'd look at these and say, these don't look anything like spheres. Why are they forming a face-centered cubic crystal? You can ask which ones form better crystals. So there's a lot of questions that we can begin to ask about this. One of the things that we were able to, I would say the breakthroughs that we had in trying to understand these systems is to say, okay, of course it's entropy maximization, but how does where is the symmetry breaking that's selecting certain crystal structures over others? And what we learned is that you can think of these entropic forces as being directional. They're emergent properties in the system. They depend on the density of the system. And I'll show you how in just a second. But we're able to characterize the different kinds of entropic bonding as entropic bonding cases that map to what you normally expect in metals, in covalently bonded molecular systems and molecular liquid crystals. And it's like this local, the global entropy maximization of the system creates an effective valence for the particles that selects out certain symmetries. So we were able to quantify this, and this is work done by a research scientist in my group, Dr. Greg Van Anders, who worked out how can we quantify this and measure this directly in our simulations. And so we do this by writing down a potential of mean force and torque. This is a standard way of trying to characterize a system, because basically you have like a system, say, of tetrahedra. There's all these other particles around it. And you want to know what's the effective force and torque between two particles that are separated by a certain distance and oriented a certain way relative to each other, based on all the other particles around them. So it's a lot like there's an interaction that chemists know very well called the depletion interaction, where you say you have two big colloidal particles, two big particles in a solvent. You throw in a bunch of much smaller particles or polymers. And if you have a high enough density of these so-called depletants, they prefer to be on the outside of the two particles because there's more microstates available to them if they're not trapped between two particles. It gives you an effective attraction. It's as though the colloids are directly attracted to each other, but they're not. It's an effective, it's like an osmotic pressure. The same thing is going on here. We don't have any depletants, but our big particles are kind of acting like that. So we can calculate this. This is the free energy or the entropy of the system in the case where the Bayer interaction between the particles or the potential energy is zero, as it is in our case. And then we have this competition of two terms. The particles themselves, so if I look at any pair of particles in my system, they want to have a lot of wiggle room. But the more wiggle room they have, the less space everybody else has, the fewer number of microstates everybody else has. The rest of the system wants the pair to be like this, so that they have more volume, more possible microstates. So that's a competition between these two terms. So this term here is just the log of the Jacobian, the number of ways of forming a given pair. And for every, say, having two particles, a pair of particles separated by a certain distance and relative orientation. And for every snapshot like that, you have to calculate all the different ways that all the other particles can be. And that's what this term is. This is the free energy or the entropy, the remaining particles for the fixed pair of interest. So this is the one that scales with the pressure, and it's driving the pair to pack really densely. Okay, so those two things compete, and it allows us to now plot this quantity for the first time and visualize the effect, the directionality of the effective bonding that this entropy maximization is causing. And remarkably, we found that in the case of, say, these tetrahedra, and these happen to be truncated tetrahedra for a different system I'll talk about in a second, it turns out that at some fixed packing fraction, about 55%, but not yet in the crystal, just in the dense fluid phase, there's an effective energy of about 3 kT difference between having particles aligned face-to-face and not aligned face-to-face. So that's a strong interaction, relatively speaking, that a few kT, that there's a few kT of energy, of free energy or entropy that's driving these particles to align at their biggest faces. Okay, so assemblies versus packing. So let's get back to that now. We take our tetrahedra and we generalized it by snipping its corners all the way to an octahedron. And as you do that, and we study their self-assembly, we see that for a large amount of truncation, we still see the quasi-crystal forming. And then at some point, it switches, and now it forms a diamond crystal. And then it switches, and it forms a high-pressure lithium crystal that's a bipartite structure, like interpenetrating identical networks with 16 particles in the unit cell. Then it switches, it forms beta tin, and then it forms a BCC crystal. And then eventually a sheared BCC crystal. Those are the assemblies. I look at the packings, and we already learned that for the quasi-crystal, the densest packing is the triclinic dimer crystal, which has a unit cell of 4. And then now we switch to now here where you get diamond, now we have, for every one of these, the packing is different when you compare the assembly to the packing for a given truncation. Okay, so that's interesting. We can learn a lot from that in one parameter, but let me tell you what Beth Chen, then working with Daphne Glotzer, when they were both in my group a couple of years ago, we extended this study of shapes and said, let's look at this as a function of two parameters, two shape parameters, and see if we can plot the equivalent of an energy landscape. So when people study problems like protein folding, they look at free energy landscapes. When people study glasses, they look at potential energy landscapes. So we wanted to look at a packing landscape as a function of shape space. So that means let's plot the densest packing fraction and what forms, as a function of the particular shape. And so they studied this, we studied many families of shape. We actually studied over 55,000 different shapes and grouped them into families. So here's a particular family that includes that family of tetrahedra to octahedra. By truncating both the corners and the edges, we then get this two-dimensional family of shapes. And this is the packing landscape above it. This shows the densest possible packing that we were able to find for every one of these shapes. And then this is just looking at it straight down. And what you notice is that there are, so every one of these lines indicates a transition from one structure to another. And there's actually 3 times of transitions. You can have valleys, you can have ridges, you can have different types of first or second order transitions between structures. But I don't have time to talk about that. The key thing is that there are whole regions here, like in the middle here, where I can change the shape a lot and not change the structure at all. So the same structure will maximize the packing. But then there are some places in shape space where I change just a little and I go from structure to structure to structure to structure. That's something that you cannot know a priori just looking at a single shape. You have to look at a shape and its surroundings. So this is just another rendering of the densest packings that we can look at the assembly landscape. We can say, okay, now let's take each one that we found the densest packing. Let's do these stochastic simulations and get the assemblies that form, and then we can compare them. So this is now the assembly landscape for that whole family of shapes, and then we can compare them one against another. Packing on the left, assembly on the right. And what's interesting is that we see that over that for the most part, where the packing landscape is simple, the assemblies are the same as the packing. Where the packing landscape in shape space is complicated, the assemblies are almost never the same structure as the packings. So this teaches us that, I mean, it still doesn't allow us to take an individual shape and guess or just anticipate in some way what the structure will be, or whether the structure will be the same as the packing or not. But if we simply perturb a little bit in shape space, then we can predict whether or not the densest packing might be the same as the assembly. Okay, so we reframe the question. Ask not, what is the densest packing of my shape? Ask instead, what does the densest packing surface look like in the neighborhood of my shape? So that's a key point I want to try to drive home, is this idea of thinking in terms of shape space. But okay, let's think about encoding of information. The key point is I want to be able to, through shape, encode information for what the resulting structure should be. So can't I do that by saying, okay, I take a crystal structure. I know that I can construct it's Voronoi cell, right? I can do a Voronoi tessellation like this. I can take a structure like an arsenic structure, and I can create what the Voronoi tessellation is. And let's say that there's one Wyckoff position, so there's one shape of Voronoi cell. Let's call that shape a particle. Let's make it a hard particle. Then I know, like a jigsaw puzzle, if I put those hard particles together, by definition, I will have a particle that packs with density 1. That's the densest packing. So I've just created that. So now let's just take those shapes and do a stochastic simulation at much lower densities and see, does that Voronoi particle, that Voronoi shape, self-assemble in the same structure or not? So we studied that for a number of different systems. And of course, we found that sometimes yes, sometimes no. Sometimes it works, sometimes it doesn't. But let me show you some interesting cases. Here's a case of beta uranium. We start with this complicated structure, and we say, let's create the Voronoi cell. So beta uranium has 2 types of Voronoi cells, these blue ones and these gold ones. And they have to have a particular position relative to, and orientation relative to each other to fit together perfectly to give you back the structure that you started with. So we take those 2 kinds of shapes, and we throw them in a box. We do Monte Carlo simulations and see what comes out. And what is really interesting is that we get repeatedly back the beta uranium crystal structure, meaning if I look at the centers of all the particles, they sit on the same lattice as the original target lattice that I constructed the particles from. Great. Except that there seems to be no, there's disorder in what's the word I'm looking for right now? There is compositional disorder. The blue and yellow particles, the two different types of Voronoi cells, the two Wyckoff positions, are not where they're supposed to be. They're not ordered. In order to take, so I cannot take this system and densify it to packing fraction 1. I'd have to move them into the right place. And yet, there's enough information encoded in the local entropic valence of these particles to still give me back the structure even with some disorder in the composition. That's remarkable. Am I done? Okay. So I will conclude by skipping all of that and just leave you with a couple of questions, which is, how do we extrapolate this now? Can we use this information now to design building blocks that will give us arbitrary structures that we want? Is it possible with entropy alone to get to obtain every known crystal structure, every known space group, right? So we're working through the 230 space groups. We've already recovered about 45 of them just from entropy alone. Which ones can we get? Which ones can't we get? And why? What's special about those? What about chirality? Can we encode chirality through entropy and understand what the role of entropy might have been in early stages of chiral symmetry breaking? There are many problems in biology where there are shapes and there's crowding, and we know that there's thermal motion, we know that there's entropy. So in what ways are we underestimating the role of entropy in a lot of biological and other processes? So I'll leave you with those questions. Thank you.